Welcome to the Unit 4 calculator video for polynomials for Honors Algebra 2 Trig. So what we're going to do is we're just going to go through problems 1 through 4 on your worksheet. And I'm going to try and do it as fast as possible because it could take a long time if I'm typing everything in. So I have already typed in problem 1's points. And so then I'm going to go to Stat, Calculate, and then this is asking for a cubic equation of these 4 points. Now, one thing that we need to know is that if we have 2 points, we can create a line. And anything more than 2 points, we can create a regression equation of a line that as long as those points aren't on the same line, we can get a line that approximates where those points are. Last chapter, we did quadratic regression. And so if we had 3 points, we can get an exact quadratic equation. Anything less than 3 points wouldn't work. And then anything more than 3 points, if they don't completely match the parabola, then we get a best guess parabola. Well, as would make sense, if 2 points make a line and 3 points, as long as they're not collinear, make a quadratic, then 4 points can make a cubic. So since in this case I have 4 points and it's asking for a cubic, this will give me a perfect representation of a cubic equation. So I go to cubic regression, that's option 6. And then L1 and L2. I want to store my regression equation in Y1 if possible. So vars, yvars function Y1. Again, if you don't have this screen where you can store it, you have to actually type it into your Y1 yourself. And then we'll hit enter and calculate. And so we end up getting this regression equation. Negative 1/5 x cubed minus 7x squared plus 22x minus 11. So that ends up getting stored. Oops. I have that from last video, but it ends up getting stored. And again, there's a slight calculator rounding error. Notice it's after about a ton of zeros, so you don't have to worry about that too much. And so then we want to graph this, and well, clearly this is not going to be a very good graph for us. So we have to find a window that's going to work. I've done this a few times, so I know where everything is going to be on this particular problem. I've kind of investigated it in advance. So if I make my x negative 50 as my min and my max 10, that'll work pretty well. If my y min is somewhere around negative 1,000 and my y max is somewhere around 1,000, then everything will work out okay. I've never talked about scale on a video before, but scale is basically where all the tick marks are. So if I change my scale, that can make the tick marks not feel as daunting. Oh, and I didn't even go low enough. So I did it, but I screwed up. So my y min needs to be around negative, I think 2,500 it was. So I kind of forgot. So if I'm looking, this is kind of what my graph looks like. And so now it's asking me for regions where it's increasing, decreasing, positive, and negative. So in order to determine where things are increasing and decreasing, I'm always moving from left to right. And so if I'm moving from left to right, what I'll notice is this function is decreasing, and then it reaches some sort of minimum value. Now, that's not the absolute minimum or maximum, but that's the value where it stops decreasing and starts increasing. So this is what in calculus you will call a local minimum. So it reaches this local minimum, and then it starts heading up until it gets to this point, and then it reaches what is called a local maximum, and then it starts heading down again. So it is decreasing, then increasing, then decreasing. So we can find those by doing second calc and then finding the minimum and maximum values. So I just need to make sure that I bound my minimum, and I definitely bounded it. So it's going to find it. And so this function is decreasing from negative infinity until negative 24.812. Then after that, or 24.811, my fault. So then after that, it's going to be increasing from negative 24.811 until we get to this maximum. So I'm going to second calc, find this local maximum, and then bound the maximum, and it finds it at 1.478. So it is increasing from negative 24.811 until 1.478, and then it is decreasing forevermore thereafter. So it will be decreasing from 1.478 until infinity. I'll show you what that looks like in interval notation in a minute, but that's kind of visually what's happening. And then I need to figure out regions where it is positive and negative. So the graph is positive anytime it's above zero and negative anytime it's below zero. So we want to find zeros. And just a reminder that if I type in a number when it's a zero, I don't think it actually works, or at least it didn't work last time I tried it. So I need to bound. Oh no, that was intersection. So I could have done this. I just kind of wasted your time by scrolling. So I find a zero at negative 37.938. It is positive from negative infinity to negative 37.938. That sounds kind of weird that it's positive from negative until negative, but we're reporting x values where the y values have what the question is asking about. So the x values where this function is positive are negative infinity to negative 37.938. Then it's negative, the function is negative from negative 37.938 until it appears the rest of the time. But we should probably zoom in on what is happening around zero, because I'm guessing that there is something that's happening that Mr. Mead wants to teach us. And if I zoom in around zero, notice that the function actually does go above the x-axis here. So I need to find those values as well. So I have, oh no, my fault. So I bound it between 0 and 1, and I find a 0 at 0.627 or 0.628. So that means that it is negative, the function is negative, from negative 37.938 until 0.628. And then it is positive from here until we have another 0 that we have to find. And so I'm going to bound my 0, and then it is at 2.310. So that is the last spot that it is positive, and then it's negative thereafter. And so if I look at problem 1, this would be all of the stuff that I would write down. These would be the answers that I report. So here's my equation. It was decreasing from negative infinity to negative 24.811. Then we reached a local minimum where it started increasing from negative 24.811 until 1.478. And then it was decreasing from 1.478 until infinity. It was negative, I'm sorry, it was positive. The function was positive from negative infinity to negative 37.938. It was negative from negative 37.938 until 0.628. And then it did that thing where it just barely went over the x-axis. So it was positive on this interval here, and then it became negative after 2.310 until infinity. So remember, we are reporting the x values for which the y values are doing these things. I've now typed in problem 2, and so we'll talk about what happens here. I have 5 points, and it tells me I want a quartic, so that's going to give me a perfect quartic equation that actually matches all of those points. I'm going to once again store this regression equation in y1, and I'm going to calculate it. So this is kind of what that function looks like. And it is stored here. So it's 1/20th x to the fourth minus x cubed plus 5x squared minus 2x plus 10. And then I'm going to turn my stat plot on and then zoom stat. And this won't give me, well, it actually does give me everything I need to know. Well, not quite, because there's going to be another dip-de-doo going up here, and then I'm going to have to find another intersection with the axis. But notice that these points are perfectly on the graph. Um, all of those points are perfectly on the graph because it's the exact amount of points 5 that would end up giving me a cubic equation. So let's talk about the increasing, decreasing, positive, and negative. The function is decreasing from negative infinity until I get to this local minimum value. So let's find that local minimum value. It looks like if I bound it between -2 and 1, I'll find my local minimum, and that will occur at 0.213. So I'm decreasing from negative infinity to 0.213, and then I will be increasing until I get to this local maximum value. So second trace maximum. Also make sure I'm on Y1 and I'm not on the stat plot, because if I'm on the stat plot, then that won't really help me out very much. So I want to make sure that I bound this effectively, and then it gives me the answer of 4.597. So I'm increasing from 0.213 to 4.597. Then the function will be decreasing after that until the next local minimum. So I want to bound my local minimum, and that occurs at 10.189. So I'm decreasing from 4.597 to 10.189, and then I'm increasing forevermore thereafter. Now I have to change my window slightly, make my x max maybe 16 or so, and then this will ensure that I see where the function crosses the axis. So the function is positive from negative infinity until this 0, so that's somewhere around 8. So I will find the 0 there, and I will bound that 0, and it appears that it is at 8.605. So the function is positive from negative infinity to 8.605. Then the function is negative from 8.605 until 11.403, and then it is positive thereafter. So if I look at number 2, here's all of the information that we just talked about. We found the function, we found intervals where it was increasing and decreasing, positive and negative. If we look at problem 3, this problem is talking about Canadian gas prices starting in 1979. And I could do this on the TI, but Desmos also does it, and I'll do one problem on Desmos just to kind of show you what it looks like. So if I type in all of these points, notice it's more than 4 points and it's asking for a cubic. So more than 4 points and asking for a cubic, that's not going to give me an exact curve that matches all the points. So if you look, clearly the curve doesn't intersect all of the points, and as a matter of fact, it doesn't intersect any of the points, because at 14, even though that one looks like it's pretty close, it's still not exactly on top of it. So it doesn't match any of the points, but it gives me the best fitting cubic curve for these data points. And so if I look, this is what I have, 0.0122836 x cubed minus 0.464517 x squared plus 6.29503 x plus 23.4516. That gives me the curve, and I've labeled it as h of x on my Desmos. So I can answer the questions accordingly. It's asking for the data in 1985. So if I'm looking at 1985, that would be when x is 6. So if I say h of 6, that'll give me the value of 47.152. So that is 47.15 cents per liter, so to speak. And So that's kind of what we have there. That would be the approximation. That's also an interpolation. So the difference between an interpolation and an extrapolation, an interpolation is something that occurs within the known data points, and an extrapolation is something that occurs outside of the known data points. So when it asks us for information from 2019 or 2029, that would be an extrapolation. We'll talk about that in a couple problems. Then the next thing that it's asking about is when the uh, when will this end up being about 56 cents per liter? And so what we can do is we can take y equals 56 because that represents cents per liter, and then we can figure out where that intersects the curve. That intersects the curve at 16.465 thereabouts. And so that would be around 16 years. And so 16 years after 1975 would give us 1995. Then finally, it's asking us what is the prediction of the model when we get to 2019 and 2029. So 2019 would be 40 years after the model, and that would be 318.176 cents per liter. And 2029 would be 712.361 cents per liter. Again, I'm rounding to 3 decimal places as much as I can. So if I look at the answers here, this is what we have. So we wanted to find the intersection of the model in part B of f of x and 56. Also notice that, excuse me, I'm sorry. Also notice that this model is not very good at extrapolation. And actually, most models are not good at extrapolation, which is trying to find something that's outside of the data that we actually know. We do know that in 2019, the gas prices in Canada were averaging out to be 114.6 cents per liter. That's nowhere near 318 cents per liter. And that's because most models are pretty good for the data that they know. But once you get outside of that, the model ceases to be any good. One last thing about problem 3 is that if we want to do this on Desmos, I didn't actually tell you how to do this. So you can take x1 and y1 and type them in here, and then put y1, then the tilde, and then put a bunch of coefficients in front. Never put e because it will calculate e as a number, but put a, b, c, d, then you can skip to f, g, h, I, whatever. Actually, don't put I because that might think it's the imaginary number. But you can put these things, then put x1 cubed, x1 squared, x1, and so on. Now, if you had x2 and y2 in here, you would have to change what's in here. But if you just type this, Desmos will do the regression for you. For the Brook problem, so stat, quartic regression, since it's asking for a quartic model, notice that this will end up perfectly matching up because it's exactly the amount of data points for the quartic model. I'm going to save this as my y1. Then I'm going to calculate. And I get 6x to the fourth minus 140x cubed plus 1060x squared minus 2500x plus 11750. So if I make sure, and my stat plot's on, so I'll zoom stat and see if it gives me everything I need. It may or may not, depending on the questions. So one of the questions is to find the value at 8. So I want to trace, make sure I'm on the curve and not on the points. Then type in x equals 8, and it will tell me that the model is predicting 12,486 Brookie bars sold. The next thing it's asking for is to find the first month where 14,000 Brookie bars are sold. So I will type in 14,000 for Y2, graph that. Notice it's not on my graph, so then I have to change my window. And clearly it's not going to be shown. I'll increase the X max just a little bit just to make sure. So I'll make Y max 15,000 as well, so I can definitely see it. So there's my 14,000 line, and I want to figure out where that intersects. And intersect is the one that I'm not allowed to actually um, type anything in for. So I just have to scroll with it, scroll with it. Okay, I'm pretty close. So I hit enter 3 times, and it's going to tell me 10.992 is my X value. So that's the month. And so I would say that since the question is asking for what is the month that it's predicting more than 14,000, I would say the 11th month. And so here are my answers for the Brookie problem. Uh, we have this curve. This is the bars predicted. And then we take this, find the intersection of the curve and 14,000, and see that it's in the 11th month.